Welcome to the Explainer. Today, we aren't just staring at dry equations on a chalkboard. No, we're stepping right into a virtual lab to dissect the exact moments when matter violently and beautifully transforms right before our eyes.
But before we start randomly mixing things together, I want you to think about a pretty fundamental question. If you mix two things in a beaker, how do you actually know a chemical change has happened? What are the physical, undeniable clues that tell you the atoms have completely rearranged themselves? Take a quick second to picture it.
Okay, let's dive into this. When you're hunting for physical proof of a reaction, you're looking for four main clues. You might see the sudden evolution of a gas. Think furious bubbling or fizzing. You might witness a dramatic change in color. You could literally feel a change in temperature, with the glass getting suddenly hot or freezing cold, or you might see the formation of a precipitate, which is basically when a solid just suddenly appears out of two clear liquids.
Here's the mental map for our explainer today. We'll start by spotting a reaction, then explore combination and decomposition. Next is the displacement battle, unlocking redox reactions, and finally, chemistry in everyday life.
Section 1. Spotting a chemical reaction. Let's get our virtual hands dirty with our very first experiment.
Imagine holding a thin metal ribbon over a burner. When this specific metal ribbon burns, it doesn't just catch fire, it erupts with this dazzling, intense white flame, ultimately crumpling into a fine white ash in the watch glass below.
So let's look at the specific steps to see what's actually happening. First, we absolutely have to clean the ribbon with sandpaper. Why? Well, because this is magnesium, and in the air, it naturally forms a stubborn, protective oxide layer that we have to scrub off before it'll ignite. Once it's cleaned, we burn it. That's our reactant X, magnesium. It reacts with the oxygen in the air to form reactant Y, magnesium oxide. A dull metal just turned into blinding light and white powder. Now that is a spectacular chemical change.
Moving right along to Section 2, Combination and Decomposition. Let's look at the grand architecture of these reactions and how elements either team up or violently break apart.
Now check out the sheer invisible power at play here. Water is being added to calcium oxide, which you probably know as quicklime. When these two mix, they form slake lime. But notice the bubbling and imagine feeling the heat radiating off that glass.
This brings us to a really fascinating scientific reality. The assertion is that mixing quicklime and water is an exothermic reaction because it reacts vigorously and releases a large amount of heat. And guess what? Both of those statements are absolutely true. The chemical bonds themselves release so much heat that the water can literally start to boil with no external burner required. That's an exothermic combination reaction in its purest form.
One of the students we're following today, Dilip, was trying to compare combination reactions with decomposition reactions. The easiest way to help Dilip out is just to put them side by side. They're exact opposites. Combination is kind of like a marriage. Multiple reactants join up to form one single product, exactly like our quicklime and water. Decomposition, on the other hand, is a messy breakup. A single reactant completely shatters into multiple different products.
And honestly, there is no better example of this messy breakup than the electrolysis of water. We are forcing a single reactant, water, to break apart. Because we have to actively pump electrical energy from a battery into the water to force this breakup, this is an endothermic process. It requires energy to happen, actively splitting the water into hydrogen gas on one side and oxygen gas on the other.
And the chemistry is so incredibly precise. It's basically mathematical. When water breaks down during this electrolysis, the mass ratio of the hydrogen gas to the oxygen gas liberated is exactly 1:8, every single time. It's like a beautiful hidden code governing the water we drink every day.
Now, let's head into Section 3, the power of displacement. This is where chemistry gets competitive.
In this classic experiment, a standard iron nail is dropped into a bright blue solution of copper sulfate. If you just leave it there for a few hours, the blue color completely fades away, turning pale green, and the iron nail gets coated in this rusty, reddish-brown deposit. The iron is literally kicking the copper out of the solution and taking its place.
But this doesn't just happen randomly. Let's test your intuition for a second. Why would dropping zinc into dilute hydrochloric acid cause violent fizzing, but tossing a copper coin into the exact same acid does absolutely nothing?
So, the crucial point here is the reactivity series. Think of it as a chemical hierarchy. Zinc is highly reactive. It's strong enough to bully the hydrogen out of the hydrochloric acid and take its place. Copper, however, sits way down at the bottom of the reactivity series, well below hydrogen. It simply isn't strong enough to displace it. In the world of displacement, the reactivity series dictates the winner, every single time.
Let's shift gears now into Section 4, Unlocking Redox Reactions. Time to unpack oxidation and reduction. Consider this equation. Zinc oxide plus carbon yields zinc plus carbon monoxide. Watch what the carbon does here. It acts like a chemical thief, a reducing agent. It forcefully strips the oxygen away from the zinc oxide, leaving pure zinc behind. Meanwhile, the carbon proudly walks away with the oxygen to become carbon monoxide.
The rules here are incredibly strict, but pretty straightforward. Oxidation means gaining oxygen or losing hydrogen. Reduction is the exact reverse, losing oxygen or gaining hydrogen. But the absolute most vital rule, they always occur together. You literally cannot have a theft without both a thief and a victim. If one substance is reduced by losing its oxygen, another substance must be oxidized by gaining it. They are inseparable partners in the chemical dance.
Let's bring this all together in Section 5, Chemistry in Everyday Life.
Think about the kitchen in your favorite restaurant. If they leave a bottle of cooking oil rich in unsaturated fats sitting out near an open window, after a few weeks, that oil acquires a foul, nasty odor. Why? Well, it's oxidation. The exact same process that rusts metal is reacting with the fats in the oil. This phenomenon is called rancidity. These chemical principles directly affect the food we eat and how we have to store it.
Here's a fascinating biological twist for you. We learned earlier that exothermic reactions, like mixing quicklime and water, release massive amounts of heat rapidly. Well, human respiration, the way our very cells process energy, is also an exothermic reaction. So why doesn't taking a deep breath cause a sudden, dangerous rise in our body temperature? It's because respiration is a controlled, step-by-step biological oxidation. The energy is released slowly and carefully stored in molecules, rather than just bursting out all at once as raw heat.
And that brings us full circle, from the brilliant white flame of magnesium in a lab to the fizzing of zinc and acid, right down to the oil spoiling on your kitchen counter and the air in your lungs. Chemical equations aren't just dry facts you memorize. They are the hidden, continuous code of the universe, constantly shifting and transforming the matter all around us.
I'll leave you with this final, provocative thought. If simply leaving a white crystalline solid, like silver chloride, out in the warm sunlight is enough to trigger a chemical reaction that releases a gas, what other invisible reactions are being triggered around you right at this very second, just by the light shining through your window? Keep questioning, and I'll catch you on the next explainer.